Alright, so first of all, I'd like to thank the organizers of this wonderful program. Today, I'd like to discuss the entropy transfer processes in kinetic plasma turbulence and zonal flows. Actually, this presentation is based on the collaboration work with Hideo Sugiyama, who attended this program on the first week, and also Masanori Nunami and Moto Nakata. Sorry. Okay, the topic of my presentation is the fine structures of the distribution function in the phase space. Okay. As everyone knows, the fine structures of the distribution function can be spontaneously generated in the phase space in weakly or collisionless or weakly collisional brightness. Generally speaking, the shear operators found in various types of kinetic equations can generate fine structures. Suppose the shear flow here, depending on one of the phase space coordinates zi, is stretching the distribution function in the phase space, because zi and zj can be independent of each other, and then this shear flow motion in the phase space stretches the distribution function. One of the simplest example of this operator is the well-known linear parallel advection term, which is responsible to the ballistic mode and of course the Landau damping, linear Landau damping. And also, in case with nonlinear acceleration term in gyrokinetic or Brazov equations, nonlinear wave particle interactions can also stretch the distribution function, but in a different direction, to this linear parallel advection term. 5-6 years ago, we have studied the parallel advection effect, but in the E cross B turbulence flow, okay, where we need to take account of the growth of the effective wave number, which can enhance this phase mixing effect. Okay. So, since when we studied this problem, frankly speaking, no one was interested in this at least only a few people were interested in.
I was interested.
All right.
I was interested.
Okay.
All people who were interested are in this room.
Yeah. I'm very happy the number of the people are getting increased. So let me briefly review or say this work in the first half of my presentation. And recently, Alex and Tomohiko Watanabe and Gabe Wang and their co-workers are intensively working on the equal phase mixing effect due to the difference of the finite gyro radius in the E cross B turbulence. And also, generally speaking, it may be possible to find the phase mixing due to the magnetic drift term as well as the Miller force term. Okay. So,
I think that was the subject of Gabe's poster.
Yeah, I did it there. So, and also, okay, before going to the details, let me first propose to note on the quantity, so-called entropy variable here. So the name itself is not a matter, so many people call this quantity in several different ways. But here, the important point is this quantity is defined by means of the quadratic integral of the perturb distribution function, and then it can reflect fine structures of the distribution function, not only in the real but also in the velocity space. Okay, this quantity, entropy variable, could be a good measure for fluctuations of the distribution function in the phase space. Okay, and why this is named entropy variable? Because that is related to the second order deviation of the macroscopic entropy from the microscopic entropy defined by the total distribution function F. Okay, here is the outline of my presentation today. First, I'd like to revisit the entropy production, transfer, and dissipation processes in the slab ITG turbulence. Okay, and also I'd like to briefly mention to the relation between the kinetic simulation results and the fluid kinetic fluid closure model. And then let me come to the more recent topics on zonal flow dynamics and the entropy balance in toroidal systems. Okay, now let me go to the summary. Okay, the first topic is the slab ITG turbulence. Here we consider a very simplified model with two-dimensional real space with tilted magnetic field. Okay. In order to make the problem simpler, we have assumed the distribution function in the perpendicular velocity space to be Maxwellian, and then integrated the Gyrokinetic equation by hand, and then we can derive this simple kinetic equation, model Gyrokinetic equation. Here the phase space is reduced into three-dimensional. Okay. 2 dimensions for real space and 1 dimension for the parallel velocity space. Okay. One of the benefits of this simplification is the following, twofold. One is we can utilize a very high resolution for the parallel velocity space, because we can say reduce the total computational cost by simplifying this equation. And the second point is to decouple this system from the complicated FLR phase mixing. That is the topic of their current research. Okay. So if we have the VPAP dependency, nonlinear FLR phase mixing should appear here. But by using this simplified model, we can decouple it from this problem. Okay. And also we have made further simplification. Here we have excluded the zonal flow components. Okay. Because in the slab system, zonal flow usually completely suppresses almost all of the turbulent transport. But in order to mimic the system with larger transport flux, such as the toroidal system, we have considered the sort of the Genanken experiment, consider this system with no zonal flow case. Here the electrons are assumed to be adiabatic. So the problem is very simplified from the original one. But it should involve some essence of the collisionless or weakly collisional plasma turbulent transport. Okay, here is the result, and we see the saturation of the ITG turbulence and transition to the ITG instability and transition to the turbulence. In the turbulent nonlinear state, we can see that the very fine structures of the distribution function continuously develop in the velocity space. In order to quantitatively discuss the nonlinear stage, we consider the entropy balance equation directly derived from the model Gyrokinetic equation. Okay. This is just obtained by taking the multiplication of F tilde over Fm on the both sides of the original equation and then take the phase space average. Okay. The left hand side we have time derivatives of the entropy variable and the potential energy. On the right hand side we have turbulent ion heat transport flux and the collisional dissipation term. Okay. Because of the self-adjointness of the linear collision operator, we can see the sign of this term D is negative definite. Okay. All right. So we have checked the time evolution of the entropy variable for the purely collisionless and weakly collisional cases with different ion-ion collision frequencies. you can see the delta S can secularly grows in time, while in case with finite collisionality, it saturates at a certain level here. Okay, and in the collisionless case, we could find the balance of the linear growth of the entropy variable with the turbulent transport flux. Okay, but in the weakly collisional case, we have seen the saturation of the growth of this entropy variable, and then we have found the balance between the transport flux and the collisional dissipation. Okay. Even with the very fine small values of the collisionality, it should play an essential role in determining the final saturated turbulent state of the system. But fortunately, for the sufficiently small values of collision frequency, we have found the transport flux itself is almost the same between these two cases. It was not trivial thing, but it has been found by carrying out the parameter scan for the wide range of the collision frequency. Okay, now from this result we could derive a scenario on the entropy production, transfer, and dissipation processes. Okay, it is summarized in this chart. Turbulent heat transport can produce the entropy variable on the macro velocity scale. Okay, that because the transport itself is given by the turbulent flow and temperature fluctuations. Both of them are given by the low order moments of the distribution function. Okay, the produced entropy is transferred to micro velocity scale, and then in the purely collisionless case, the growth of high order moments continues, and we have found the so-called quasi-steady state of the kinetic turbulent transport. Here, quasi-steady means the transport flux looks to be in a statistically steady state, while the distribution function continues to grow, continues to develop into finer and finer scale, very finer velocity scales. But in weakly collisional case, we have found the balance of the collisional dissipation with the entropy production, or in other words, the turbulent transport. Okay. And then finally, we could find the real statistically steady state. So in this process, we presume the scale separation between these two processes. Okay, entropy production should be found on the macro velocity scale, but dissipation should be found on the micro velocity scale. In between these two scales, we anticipate appearance of the scale-free region that should be closely related, or say should be understood in analogy to the inertial subrange of the neutral fluid turbulence. Okay, now let us consider how to analyze the spectral of the distribution function in the velocity space. Okay, it was actually done by utilizing the Hermitian polynomial expansion of the distribution function for the velocity space. Here we employ the Maxwellian wave function, and then this expansion could be orthogonal. Okay, and yeah, here the entropy variable density at certain n is given by this expansion. Okay, here the summation k, summation over the wave number k is taken here, and then we can derive the entropy balance equation for the entropy variable density in the n space. Okay. Here, this is the first term shows the entropy growth of the entropy variable, and on the right hand side we have the dissipation term coming from the collision operator. Okay. On the right hand side of this equation, we have these two terms. Here, J denotes the entropy transfer function from the macro to micro velocity scales. Okay. This finite difference between Jn minus half and Jn plus half corresponds to the divergence of the energy transfer function formulated in the energy spectral equation of the neutral fluid turbulence, isotropic and homogeneous neutral fluid turbulence. Okay, so the flow of the entropy variable is schematically shown here. It is entropy variable is produced on the macro scale, macro velocity scale, or say at low n number, for example n equal 2 here, and then it is transferred towards the high n numbers through this transfer function, and the difference of these two functions should balance with the collisional dissipation on micro velocity scales. Okay, actually we have found the power law scaling in the entropy density spectrum. Okay, here we plotted several lines for different values of the collision frequencies. Okay, and on the low n side, we have all these results look the same because that is governed by the turbulent transport process itself. Okay, and then produced entropy is transferred towards the micro velocity scale, and then on the micro scale or high n side of the spectrum, we can find the exponentially decaying spectrum of the entropy variable density. So how to characterize this spectrum? That is the next problem. But before going to the scaling, let me show you the plots of the transfer function, entropy transfer function J. So certainly in the power law scaling region, we can see the very wide and flat profile of the transfer function J. This has a very strong analogy to the neutral free turbulence energy spectrum, where we should find this, say, flat profile of the energy transfer function in the k-space, where no production nor dissipation occurs. That's why this process should be scale-free, and we have found the power law scaling in this region. Okay, so now let me consider the scaling of the entropy density spectrum here. In analogy to the passive scalar convection in the homogeneous isotropic turbulence, we presumed the exponential growth of the effective wave number in the turbulence, because E cross B flow can quickly stretch the fine scale structures of the distribution function in the real space. That increases the effective wave number. The increased effective wave number simultaneously enhances the phase mixing, because the phase mixing, parallel phase mixing is proportional to the real space wave number k. Okay, by taking into account of this effect, we could derive this analytical formula. Okay, here the exponential function is showing the collisional decay of this spectrum on high n side, but in the low or intermediate range, the spectrum is expected to follow 1 over n. Here sigma denotes the entropy input or total dissipation of the entropy. Both are the same. And we can see this equation shown here by the dashed line, dashed curve, is fairly agree well with the simulation results shown here by the solid curve. But we simultaneously have found a deviation of the simulation results from the analytical theory shown here by the dashed curve. In order to understand this difference, we had to take account of the effect of the finite resolution in the real wave number space. Fortunately or unfortunately, this works well, and because the turbulence stretches the distribution function in the real space continuously, and then effective real space wave number can also grow in time, but we only have the finite resolution. Then finally the fluctuation of the distribution function can reaches to the finest resolution, and then this enhancement of the parallel mixing should be influenced by the finite resolution in the real space. Okay, that if we take account of that effect, the scaling is slightly modified from 1 over n to 1 over root n square root of n. Okay, that is plotted here by the dotted line. Although this formula fails to reproduce this power of scaling, but it accurately reproduces the exponentially decaying spectrum on the high n side. Okay, the situation may be summarized in this cartoon picture. Okay, by the turbulent stretching of the distribution function, the effective real space wave number of the distribution function is expected to grow with n, square root of n. Okay, but since we have finite resolution, this curve should be saturated, and then entropy flows goes towards into the high n region. Okay, then finally these fluctuations are dissipated by the collision term. This picture shows the cross sections of the entropy variable density in k and n space. Okay, the horizontal axis is showing the wave number space, and we plotted the several slices at different n values. Okay, here and here and here. So as n increases, the peak value of this spectrum rapidly decreases. But on the other hand, the tail distribution is not dissipated completely or exponentially in the high n, even in the high n region. That is maybe somewhat problematic in considering the numerical simulation with finite resolution. But I'd like to this point if you have some suggestions in considering the FLR phase mixing case, because in the FLR phase mixing case, Alex claimed the real space wave number k should be proportional to the index of p, right, of the Hankel transformation.
Yeah.
That is corresponding to the wave number of the velocity space. Okay, here index n is proportional to the square of the velocity space wave number. All right, and then here is also the real space wave number is roughly proportional to the velocity space wave number. Okay, the scaling is very similar to your case.
I think so. I think the work that we've done is primarily for the case of sublarmor scales, right? So if you look at ky larger than unity, you have this perpendicular phase mixing effect. Which incidentally we didn't discover. In fact, there's I think the first paper which realized that was Dorland and Hammett 93. They didn't quite call it that, but they were basically phase mixing in vivo. So once you have that nonlinear phase mixing, you can have a hand-waving argument for why the parallel phase mixing at those scales will be subdominant.
Yeah,
so if you accept that argument, then you have a relationship between k and the Hankel index or equivalent.
Yeah, could be for the perpendicular velocity
But
space.
at long wavelengths, there is no such argument. So if you look at phase mixing at k rho I larger than 1, less than 1,
Here,
I think you're probably right.
Yeah.
About this, right?
But I don't know which process is more dominant in the high K region or smaller scales. It could be the matter for the discussion. But my point is whether you could observe the exponentially decaying spectrum in the real K space in case where the FLR phase mixing dominates.
Exponentially decaying?
Yeah.
No,
Otherwise,
it's not exponentially. It's
no. Yes,
yes. Power law. It's a power law. It's not exponentially.
Yeah, but finally, I hope we could observe the exponentially decaying spectrum.
Oh, you mean
side.
the cutoff, the collisional cutoff?
Right.
Oh yeah, we have that. Tomo has this in his.
I haven't seen it in his paper, but yeah, let us discuss right
Well, it's in his paper, what you can see is a power law, and then it sort of curves down as turbulent spectra do.
Yes.
Right? Whether it's exponential or he didn't study the extreme deceptive range. Right? He just resolved the cutoff and then that.
Yeah. To my understanding, it was not so to date it was not so clearly found the existence of whether the collisional cutoff exists in the real wave space number in the spectrum of the entropy variable density. I'm not sure.
Well, intuitively, right? Intuitively it should, because basically if you took a collision operator, just a regular collision operator, and gyro averaged it, you would pick up terms that are both second derivatives in velocities and second derivatives in space.
Yeah.
So the collision operator will actually, there will be a bit of it that looks like diffusion operator. It's what's called gyro diffusion, right, or something like that.
Yeah, but to my knowledge, no one has clearly shown the spectrum which is showing the exponential decay on high K side.
You mean you want specifically?
Yeah.
You want.
Yeah, I want to see the exponential decay.
You want to see it exponential as opposed to just some decay.
Yeah. Otherwise, some fluctuation should be accumulated on high K side.
But almost spectra curve down, right? I mean, they go power low, and then down.
Yeah.
Is that not enough? No.
No, sorry.
Well, one could do this. I mean, it's just a question of turning up the collision.
Yeah. But we need very much high resolution for that.
No, you can just turn up the collision frequency on the existing simulations.
Yeah, but simultaneously we need to have.
You don't turn it up, right? That would sort of contract your inertial range.
But he wants to look at the dissipation range.
No, it should be coexist with the inertial subrange as well.
Yeah, but Tomo has quite a lot of inertial range, so one could sacrifice half of it easily.
Yeah. Anyway, it should be the topic. Now we can say actually concentrate on. So.
Oh, we could, Skype Tomo and ask him, ask him to give us a sort of a simulation with a bigger viscosity.
Yeah, but hopefully we could confirm the proportion, linear relation between the effective wave number and the square root of n. Okay, here.
But could I ask you something about this? Because I read your paper, right? And what puzzled me about this argument that you're making about ky, right? Is that so physically when we're talking about the parallel phase mixing, it's parallel, right? So it's k parallel.
Yeah.
Right? So then you say, okay, k parallel close to the rational source. So this is going to be related to ky. It's going to be kz minus, I don't know, something like ky, right? So and that provides you with a connection from k parallel to ky. But then you go ahead and substitute this, and then you say, but there's a ky here, and there's a ky in the nonlinearity.
Yeah.
So there's now going to be a nonlinear mixing of these kinds. And that's where
my point is through the nonlinear interaction, parallel wave number can also be simultaneously increased through the nonlinear coupling.
This looks to me like you've just projected k parallel onto the perpendicular direction.
Yeah. In this case, it is true, but even if in the general case that nonlinear coupling should occur, not only nonlinear coupling in the turbulence should occur not only in the perpendicular wave number space but also in the parallel wave number space.
Fair enough, but that's not what you're doing, right?
Yeah, but it's essentially the same.
Well, you have k perp. So there's this sort of argument which I never quite got my mind around in your paper when you say k parallel.
Yeah.
Then I'm going to fix kz, replace k parallel with ky, right? And now my favorite wave number is ky. Then I have ky sitting in my Poisson bracket, which is the perpendicular nonlinearity.
Yeah, yeah.
And now I'm going to say k perp is like ky. So now k perp is like k parallel. So we had a parallel phase mixing which was due to k parallel, and now it's
by using this
moderated by
simplified 2D model, that is only the projection of the perpendicular wave number to the parallel wave number. Yeah, you're right. But the similar coupling should also be found in the 3D turbulence as well. But of course we haven't checked it by means of 3D case. But in a 5D simulation, we can certainly find the results of the parallel phase mixing in the ITG turbulent transport. Let me come to the point later. Okay. Yeah. Anyhow, so if we have large enough resolution in the wave number space, we can reproduce this growth of this effective wave number. But because of the lack of resolution, it should finally stay saturated. Okay, but this process can be correctly, say, reproduced if we have enough resolution. Okay, now let me briefly mention the relation between the collisionless and kinetic fluid models, and the collisionless kinetic simulation result was utilized to check the phase relation between the temperature and density fluctuations, which is essentially important point in considering the fluid closure model. Okay, and then we have found the histogram of the phase angle between the temperature and parallel heat flux. Okay, this is the result of the kinetic simulation, and we have velocity space structures of the distribution function, and then measured the phase relation between temperature and the heat flux. And for the longest wavelength perturbation mainly carried in the turbulent heat transport, showing the dissipative phase relation with -π/2. But in some cases, for example, in this case, the most unstable mode has totally different nature of the phase relation. Here, the oscillatory phase relation was observed. This result is an evidence showing that, say, it is not an easy job to design a closure model, one closure model which can simultaneously satisfy these two phase relations. Okay, now let me come to the toroidal case. Okay, here we would like to discuss the zonal flow response from a point of view of the phase mixing, and also I'd like to briefly mention to the zonal flow generation as a result of the entropy transfer. Okay, this is the model gyrokinetic equation for the flux tube case. It's very simple and well defined problem. So let me quickly go through this page, and we have considered the so-called Rosenberg-Hinton problem by giving the initial Maxwellian distribution. Okay, and then the potential fluctuation is going to be decaying in time through the Landau damping of the gamma oscillation. Okay, here, this process can be rewritten in the entropy balance equation. Here, the entropy variable of the zonal flow and its sum to the potential energy should be conserved through this process. Okay. accuracy of the total conservation of this process could be a very good check for the numerical accuracy of the gyrokinetic code. And in this case, only a few percent of the total entropy is lost due to the numerical dissipation in this case. But most of the fluctuation is entropy variable is carried by the fine scale fluctuation of the distribution function growing in the passing particle region of ion velocity space. Okay. These are snapshots of the distribution function in V parallel and V perpendicular space. Okay. And this is a trapped particle region, and this is passing particle region. Okay. You can see fine scale structures develop in the passing particle region, and then but simultaneously in the trapped particle region you can see a coherent structure of the distribution function. In this panel we plotted the analytical solution of the bounce averaged distribution function of the solution of the Rosenberg-Hinton problem. Okay, if we subtract this solution from this numerically obtained results, you can see the fluctuating component only here. So this means the obtained numerical result is given by the sum of the analytical solution and these fine scale structures which are responsible for collisionless damping of the gamma oscillation. Okay. This is a tokamak case, and in helical system 3D geometry we have an additional shielding term of the zonal flow potential, which is associated with the motion of helical ripple trapped particles drift, and then the additional polarization effect appears in the analytical expression of the zonal flow response function. Here this is due to the polarization effect of the helical ripple trapped particles. But interestingly, this polarization effect has a weak time dependence as shown here. Okay. Here the summation is taken for the trapped particles only, and this is the contribution from the electrons, so you can we neglect this part here. But the point is shown here. Okay, so on in the index of the exponential function, you can see the origin of the phase mixing of the zonal flow potential due to the slow radial drift motion of the helical ripple trapped particles. Okay. Then as time goes, the fine structure develops in the velocity space, and then this part becomes smaller after taking the velocity space integral, and then contribution of this epsilon approaches to the unity. This part becomes dominant only, and then the denominator increases and reaches to the final value. Okay, this process has also been simulated in by using our gyrokinetic code. Here we consider the full 2D velocity and one-dimensional parallel real space coordinate. Okay, you can see the very fine structure develops in here and there in the passing particle region. This is associated to the passing motion of particles through the helical ripples. But simultaneously, you can see a mean negative part of the distribution function in the trapped particle region. This is associated with the escape of the helical ripple trapped particles, okay, due to their radial motion. This scale length becomes smaller and smaller as time increases, and then causes the phase mixing, and which results in the enhancement of the additional shielding term of the zonal flow potential. Okay, this is due to the phase mixing of the, say, radial drift motion of magnetic drift motion of the traveled particles. Okay, and now let me come back to the entropy balance equation again, but in the toroidal systems. Here we consider full 5-dimensional system, and but we can also derive the similar entropy balance equation as to that of the slab case. The entropy variable is given here, and these terms are showing the transport flux J times the thermodynamic forces, density or temperature gradients, and this is corresponding to the collisional dissipation term. Okay, this balance equation can be confirmed in the toroidal ITG turbulence in a tokamak case. Here, 4 terms are simultaneously plotted, and the blue curve is showing the transport, ion turbulent transport flux, heat transport flux, and the pink curve is corresponding to the collisional dissipation. Okay. After the saturation of the initial ITG instability growth, the entropy increase becomes very small to the other 2 terms, and then even in this case we could find the balance of these 2 terms, dissipation and entropy production. Okay. In this system we have also found the fluctuation of the distribution function in the V part and V perpendicular space. Okay, so here we may see certainly the parallel phase mixing is found in this velocity space, but simultaneously we can see the perpendicular velocity space structures as well. But at present moment we cannot conclude which process is dominant or not, but certainly both processes seem to be working together in this saturated ITG turbulence. Okay, this plot is taken from the stable region of the spectrum. Okay. So the fluctuation of the distribution function produced in the unstable region is transferred through the nonlinear coupling towards the large wave number region, which is linearly stable. Okay, here we consider the entropy transfer from turbulence to zonal flows. Okay, it is done by simply separating this summation into 2 parts. One is here the summation is taken only for the non-zonal turbulence component, and on the other hand this is taken only for the zonal flow component. Okay, then the entropy balance equation is separated into 2 equations, and by this separation the transfer function appears. Okay, this term denoted by T is showing the entropy transfer from turbulence to zonal flows. Okay, if you see the entropy balance equation for the zonal flow component, because the zonal flow never produces a transport, okay, this term does not appear on the right hand side of this equation. And if you consider the statistically steady state, left hand side should vanish in average. This means in the statistically steady state, the entropy transfer from non-zonal flow to zonal flow component should balance with the collisional dissipation. Okay. But usually, because of the self-adjointness of the linear collision operator, this is negative definite. This means in the statistically averaged state of the turbulence, the entropy transfer is monodirectional. I mean, the entropy produced by the turbulence is transferred to zonal flow in an average sense, and then it is finally dissipated by collision. Okay, this picture is checked by. Sorry, this is the more detailed description of the transfer function. Okay, here we have product of the potential fluctuation and non-adiabatic parts of the distribution function. Okay. In the fluid limit with cold ions, this term can be rewritten into a more familiar form that is given by the product of the Reynolds stress due to the non-zonal, say due to turbulence, and the zonal equals B shear. Okay. Okay, we have carried out the further ITG and ETG turbulence simulations for the cyclone basic X parameters, but with smaller shear parameter cases, and then evaluated the entropy transfer function for these cases. This is recently done by our PhD student Motoki Nakata, and he found the very strong zonal flow excitation in the ITG case, but in the ETG case, this streamer-like structure dominate in the turbulent state. But if we plot the entropy balance equation for the turbulence component, its contribution of the entropy transfer from non-turbulence to zonal flow is very much smaller than other components. Okay, here the transfer function is plotted by blue curve here. The dominant two components are the transport flux and the collisional dissipation. The situation is the same for the ETG case as well. But if we plot the zonal flow entropy balance equation, okay, the results are showing the very different behaviors for ITG and ETG cases. Here, the blue curve is showing the entropy transfer from non-zonal to zonal components again, and in ITG case, the entropy transfer peaks in the initial saturation phase of the ITG instability, and then in the nonlinear case, it is balancing with the collisional dissipation in an average sense. Okay. But its amplitude is very small compared to this initial peak. On the other hand, in the ETG case, we have found relatively larger contribution of the entropy transfer in the nonlinearly saturated state. Although simultaneously, the entropy variable itself is with very high fluctuation level, but if we could take an average of this quantity, so these two terms are roughly balancing, but its amplitude is, say, almost the same to that of the initial saturation phase. Yeah, we are currently working on the detailed analysis of this result and would try to have a chance to present the result at the next opportunity. Okay, now let me come to the summary. Okay, we have discussed the entropy production and transfer processes in plasma turbulence and transport. Okay, so anyhow, the entropy transfer from a process could be, in my personal opinion, to be a very essential ingredient in considering the weakly or collisional or collisionless plasma turbulent transport process. Thank you very much for your attention.